And again, the harder one maybe to visualize is up here, but L does equal to just 1/2 of a wavelength. We've got a quarter here and then the quarter there, and we go from a crest down to a trough. That is the definition of a half wavelength, from the crest to the trough, because crest to crest is a full wavelength here. And so this particular pattern, although it is antinode to antinode, doesn't this have the same mathematics as we just got done node to node? So here's the good news. If you ever have a problem like this, and I'll just kind of do the general equation again, and then rearrange the variables, I get exactly the same mathematical formula that I got for the node to node. So that's kind of nice. Node to node is actually the same as antinode to antinode. Now, remember, I'm trying to explain number 24, and number 24 is not quite this case either. Number 24 is even a little bit harder than this. But before I completely answer number 24, let me come back to where we had left off on the lecture, because I was showing you some sound tubes here. And so this right here, let's see, what would this one be? 1, 2, 3, 4. Yeah, 1, 2, 3, 4. So this would be n equal to 4 pattern. And what I didn't get a chance to explain, and we ran out of time, is when I pluck the guitar string, because they're tied at both ends, or in this case pinched at both ends, I get the pattern that would exist from node to node. But these guys over here, these sound tubes, here, the air is kind of trapped inside, but once it gets to the out here, it's free. And so the wave pattern that is developed inside of here, a sound tube, which is open on both ends, is a pattern like this, where it's an antinode on each side. But you can see then mathematically, it doesn't really matter whether we're talking node to node or antinode to antinode. And that's why I was kind of playing with these guys yesterday, if you remember, and we'll just listen to them again. And yeah, they're not. I hope that picks up a little bit on the microphone. But what I want you to hopefully hear, besides it's a scale, is that down here, this one is a C. It's at a higher frequency than the octave below, which is this C. And so low frequency, and of course look how big it is, and high frequency, look how small it is. And we were talking a little bit about that as we got to the end, and I said, what wind instrument plays those low sounds, and which one plays the high sounds, the high frequency sounds. And now you can see it in the math. If I continue on with this mathematics, you will see then that if I go to calculate the frequency would then be the velocity divided by the wavelength. And the wavelength, as we just solved for, is 2L over n. And so if we simplify that, we get a velocity of the wave over 2L times an n. And so looking at this, you'll see that the frequencies coming from a wind instrument is related to its length, right? If you have a big length here, if L is big, then the frequency is going to get small. And so that's what we see here in these sound tubes. That's what I was trying to tell you at the end, and I didn't get a chance to get into the math, but now I get a chance to get into the math. So this is going to be a low frequency, this is going to be a high frequency, and this one's going to be something in between. And so there is my different frequencies. Well, There's more I want to show you on that, and we'll come back to it, but I don't want to digress too far away from number 24 here. So let's then take one more step here and really finally get to number 24. Watch, let me read it. Number 24 says that you have a 2-meter long rope that is tied to a very thin string so that the end of it is essentially free. In other words, they're trying to say that you have this rope that is tied on one end. It's kind of a thick rope, so it's got a lot of weight to it, if you will. It's got a length of L, which they say is 2 meters. And on this end, there is an additional string, but that string really is there just so you can pull on the bigger string. You could put tension on it. But it is so small that it's essentially light. That's what they're trying to get at. Let me read it again. A 2-meter long rope is tied to a very thin string so that one end is essentially free. So what they're trying to say is this end of the string is tied. That's like our first discussion. It's a node. But this end is free to move. So this end is an antinode. A node. And so this problem is a hard one because it is a mixture, a combination of the one I just mentioned, which is antinode to antinode, and the earlier one of number 25, which is node to node. In fact, the best way I can illustrate it is to come back to my wave machine here and say, let me take this clamp again, and let me clamp it so that this side can't move. So now that is a node. And then this other side can move. So this side over here is an antinode. So there's the question. What kind of patterns could you get where one side is a node and the other is an antinode? And that is why this one is a little harder. Let's see if we can draw a few of these. And so I'll say, here is a dotted line of a general pattern of a standing wave. Let me just kind of draw a standard wave, a standing wave. A moment later it would look like this. Okay. And let's just ask, what kind of patterns, and I'll do 4 of them again. So one end, dot, 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 dot to the other. One end, dot, 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 dot to the other. One end, dot, 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 dot to the other. And one end, dot, 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 dot to the other. Okay. What kind of patterns could I have that where one side would be a node? That would be here where the string is tied. The big, thick, 2-meter long string is tied. And the other one is free to move, an antinode. Now, of course, we were able to keep tension on it. We'll need that. Otherwise, it would just kind of flap freely, and it wouldn't really make a pattern. So we've got to keep the tension on it, but it's free to move. And so it might look something like this. Let me just kind of look at my general standing wave pattern. Let me find a node. Okay, there's a node right there. And what would it look like if I just drew a pattern to the first antinode? Well, this would be the antinode right there. It would just be from here to here. This is the hardest one to see. I'll draw it first, though. So here's a node, and then we draw it to an antinode. And a moment later, it now goes down like that. Again, it's such a small piece of a wavelength, it's hard even to see that is a wavelength. So maybe you'll see it better with the next one I do. Okay, so let's try it again. Here's a node. Let's draw it to the end, which has to be an antinode, and we already drew that picture, so let's go to this next antinode here. Okay, so we'd have to go there, and it would look maybe something like this. We'd have to go from here, there would be an antinode, it would go down to an antinode. Now that's beginning to look a little bit like a wave. It's still, I can see, it's not even quite a whole wave though, right? It arches up and comes down, doesn't complete a whole wave yet. So that's not even a whole wavelength. And that's even less than a whole wavelength. So again, that one might still be hard to see. Let's draw the third one. Okay, so the third one here might look something like this. Where's the next antinode here? Okay, so I need to draw from here all the way to here. Okay, so another pattern that is possible would be something like that. Okay, so now that's starting to look like a standing wave pattern. I can actually see from here to here. So there's one wavelength and a little bit more. So this is a wavelength and a little bit more. Well, let me draw one more, but you can see this could go on forever, and I think you'll see it if I do then the next one. So let me draw from here to the fourth antinode, okay? And so it would look something like this. I draw 1, 2, 3, and then to the antinode. And then a moment later, it would look like that. And so this is really the key to number 24, to really ask yourself this question. What kind of patterns are possible where one end is a node and the other is an antinode? And that's not how they exactly phrase it. You've got to even figure that much out. Watch, I'll read it again. It says a 2-meter long rope is tied to a very thin string so that one end is essentially free. That's all they say, one is essentially free. You're the ones who've got to figure out, oh, they mean it's an antinode. Which, of course, the other end is a node. And then it says, what possible wavelengths would produce a standing wave? So let's see if we can see it. Again, if we call this L, the length of it, which again for this problem is 2 meters, maybe it's easier to start down here. What's this one? Well, L equals, and you can see we have one hump, so that's a half wavelength. Another hump, there's another half wavelength. And then, how far is it from here to there in terms of wavelength? Do you see that quarter again? I mean, I mentioned it way back here, but now it's real important we see it standing out from an antinode to a node, or in this case, really, a node to the antinode, is a quarter of a wavelength. So I guess this would be 1 and a quarter of a wavelength. But so I can see the pattern, maybe I should write it this way. It's a half, and a quarter. In other words, it's 2 half wavelengths and a quarter of a wavelength. That's what this one is. And that pattern shows up. Look at this one down here. You have 3 halves plus a quarter. So it's 3 halves and a quarter. And then so maybe now you can see it a little bit easier up here. Isn't this 1 half and a quarter? So it's 1 half and a quarter. Whereas this first one, which again I always think is the hardest one to see, would just be the quarter. And so 0 halves and a quarter. So this is just a quarter of a wavelength. Now there's different ways you could put this together. I'll do this, that if you kind of generalize this, you could see 0, 1, 2, 3. So if I wrote it as n half wavelengths plus a quarter of a wavelength, where n then is 0, 1, 2, 3, I would have the pattern. Now if I wanted to solve this for the wavelength, I would probably do n over 2 here, plus a quarter here, and then factor out the wavelength. Maybe to make things a little bit easier mathematically, maybe I'd get a common denominator of 4, and so that'd be a 2n plus 1, L. Then maybe I'll move this over and I'll have a 4L over a 2n plus 1 is equal to L. And so finally, it took me a long time to get here, and I hope I didn't use up too much time, but I do think this is the hardest of the semester. I think it's even harder than the geometry we're about to do, but I have had students tell me that, yeah, although this was hard, I think it was the geometry that was even a little harder. So this is on par with what we're going to start talking about today or Monday on the geometry. But this then would be the equation. And so coming back over to here, and there's a lot of ways we can answer it. It doesn't ask for one. It does say which ones are possible. It says what possible wavelengths would be produced. And about the only thing I can do then to answer this is to say, why don't I put in L equal to 2? So this becomes 8 over 2n plus 1, where n equals 0, 1, 2, 3, dot, dot, dot. And that's probably the best way to answer it. You could, of course, start putting in a pattern. So you could put in a 0, and so you would get 8 over 1. Then you could put 8 over, and then if you put in 1 here, you would get a 3. And then you could put in 8 over 5, and then in 8 over 7. And then I think anybody sees the pattern, and then you can just go dot, dot, dot. And so whether you want it in a formula type or in a pattern type, I think that's a good answer for number 24. So thank you for those of you who sent me a question on that. And I hope I didn't explain it too early. Some of you might actually be watching this before you tried the homework for 15. Maybe I should have said that at the beginning. Don't cheat yourself. Go ahead and give this a try. This is a good exercise in thinking. Although, I got to admit, if you don't see what they're really after in the question, there is no place for you to go. And so you can't really do any exercise, brain exercise, and if you don't really know where to start to figure it out here. But I do know that if you give you the answers too early, that doesn't really help you. It's like my friend who wants to help me get into shape, and he goes, look, go for a run. If you get tired, I'll come pick you up. Okay. So I run about 50 feet and I'm tired. I say, hey, come pick me up. Well, that's helpful, but way too early because it doesn't do me any good to run 50 feet. Now, maybe if I ran a couple miles and I go like, okay, now come pick me up, I'm tired. That's a little different. So my friend is helpful, but a little too helpful too early. And like I said, hopefully I wasn't a little too helpful too early. All right, well, let me clean this off the board and then finish up this discussion on chapter 16. There's just a couple more things about sound waves to point out. And I will say then, as we finish up this chapter, remember, half of chapter 16 is really taking the information that we learned back in 15 and just saying, hey, 15 we learned the general property of waves, and sound waves are just some of them. You're going to hear me say that same thing as we get started with our optics and we do light waves. I'll say, hey, look, you know so much now about waves from chapter 15. You already know half of the optics. There's other things that are specific about optics I need to show you, but you already know a lot about light waves just because you know the general property of waves. And that's what I'm trying to remind you here now, is that you know a lot of property of waves because we talked about it in 15. And this gives me a good chance to point out kind of this whole pattern thing. Do you remember that discussion on resonance? Do you remember that I had the earthquake machine sitting right here? And I said, what would happen if the driving frequency, you know, my hand, I also had that spring with the weight on it. What if the hand, the force from my hand, the rate of my hand was the same as the natural frequency? Remember how we said it would have a large amplitude and respond? Let me come back to these sound tubes again. So I've got these sound tubes out here. And of course, they're all cut to a different length. Now, they're cut specifically to a length so that what would happen is they would make different tones. Okay? And this particular one, I'll pick on F since I see that I have a tuning fork that is tuned to the note F. And this F, if you play any musical instrument, you might know that the frequency of an F, so this thing right here, is this one, 349.2 hertz. I'll just hit it here. That's an F. Now, listen carefully to the intensity. So I've got an F, and I put it in front of this tube, this tube, this tube, this tube. Ooh, there's the F. This tube, this tube, this tube. I'll go back to the F. See, this is the driving frequency, and it matches the natural frequency of this one. And so it really responds to that one. I'll try it with a different one. I got another tuning fork. This happens to be the B, and so that's this one here. And again, if you're a little familiar with the mathematics of music, it's 493.9 hertz. That's the frequency of the sound for the musical note B. And so if I strike this, maybe I'll put it up to my lapel mic, that's a B. And if I put it in front of a C, a D, an E, an F, a G, an A, there's the B. Can you tell it got louder? There. And so this resonates. In fact, if I wanted to actually make one of these, let's say I wanted to make F, how long would I make this piece of plastic tube? Now, keep in mind, and this is a lot like the two problems we did, that I have an opened end and an opened end. And so if I had some tubing, and I wanted to cut it so that it made the sound F, right there, yeah, F. So if I wanted to hear that F, if I wanted to make this tube the right length, what would I do? Well, I guess I would start with this. I would say, what is the wavelength of the note F? Now, just to remind you, we do know something about the note F. I'll hold it up again here. The frequency is the 349.2 hertz. So, knowing that it is 349.2 hertz is its frequency, and noting that when I produce the sound, most likely we're talking about the sound in air at room temperature. If you remember from the discussion yesterday, that means we're looking at a speed of about 343. It's a little warmer in here today. I'm going to go up 344. Remember we said the little formula there. And so if I go ahead and grab my calculator, this would be the wavelength for that sound. So 344 divided by 349.2 comes out to be 0.98. And then the per seconds cancel, that's a hertz, that's a per second, and I'll get meters. Now, why is that relevant? Well, remember, these little pictures I was drawing, let me draw again antinode to antinode. That's the one that was not in the homework. The homework had a node to node for number 25, then it had a node to an antinode for 24. But let me point out then the antinode to antinode. And so I'll draw it again. The fundamental one looks like this. where the length of the medium here is 1/2 a wavelength. If I tried to show you antinode to antinode, again, a half wavelength, I guess I could do it with the wave machine here. Let me take off my clamp. And so the one that's, again, kind of hard to see, low in frequency, this is antinode to antinode. But it's hard to see that that could represent a whole wavelength. If I were to draw a whole wavelength in the green, it would look like this and then continue on back up to here. So my point is that I would want to make a tube so that it was a half a wavelength long, right? We just calculated right over here that the wavelength of this is 0.98. So if you listen to this, that's this frequency. And so I should cut this at half that. All right, so what is half? So if I take 0.98 meters, divide it by 2, let's see, that would be 45, 49. So we're looking at about a half a meter, about 49 centimeters. So this tube should be 49 centimeters long. Now I'll measure it with a little word of caution. It does have a diameter. So for the sound to go 49 meters, if it, starts, say, in the middle, it goes up and hits the top, goes down and hits the bottom, and it has a longer ricochet path, if you will. So the actual length of this is going to be under 49. Let's see. So if I hold this up, put my finger on that end, looks like we're looking at about 47 here. And so I'm got a length of 47. That way the sound, as it goes up and comes back down, is actually traveling the correct path of about 49. And so that's how I know how much to cut them. And then, of course, also you can see in that equation, then the higher frequencies will be smaller tubes, and the low frequencies will be the longer tube. That was our discussion on the tuba versus the piccolo. You could also see that in just sounds of humans and voices. I think of dogs. If you go up to a friend's house or even just a neighbor, someone you don't know, you knock on the door. If you hear "roar, roar," and it's deep versus yip, 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 and it's high, you don't have to see the dog. You know the size of the dog. Because that sound is determined by the size that is producing it. Big dog, woo. Little dog, yep, eep, eep, eep. Very different in the production of the sound. Or young kids, when they scream, especially infants, and think of my kids, all of them when they were, under 1, it just seemed like when they would cry, oh my gosh, it was just ear piercing because it was that high frequency, and they're just little tiny babies, and so the sounds produced from them are these really high frequencies. All right, well, one more thing here. We better close up this chapter and move on. We'll come falling even further behind. But I really thought it was worth the time and the effort, because that goes really deep. In fact, I was thinking about that. Just, I want to cover that. It's good that you get exposed to it, even if you don't fully understand it, because I do the same thing in Physics 123. And it's hard then for students to kind of comprehend it. So it's good to kind of get maybe a little bit under your belt right now, and then maybe more so when we get to Physics 123 next spring, and hopefully we'll be on campus next spring, and we'll be face to face as we are dealing with this. But there is one more thing here. Let's see if you can kind of understand the concept. Maybe I'll just start right here with this tuning fork that I was using last time. If you remember, this was 1024. So if I activate it, maybe hold it near the lapel mic. Got it? Okay. That you can hear this high frequency. If I tried to draw a picture of this, it might look something like this. Maybe I'll just put a little circle here and put an S for the source of the sound. And so maybe I'll just make these little arcs as the sound spreads out. And maybe what I'm really drawing here is the crest of each wave. And so each little arc represents a crest, so the distance from one crest to another would be a wavelength. And of course, we could actually calculate its wavelength. I'm not going to worry about that. But if I was then standing here and being the listener, I'll call this O, the observer. And so I got a couple of eyes and a smiley, and the important thing is I got some ears right here. And so the sound is coming to me, and these crests are hitting me 1,024 times every second. So boom, 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 and 1,024 of them hit me. What would I hear if I was moving? Let's just say I was running towards the source. And so I am moving this way. See, as I am moving this way, I would say that more than 1,024 would come to my ear. Now, how many more would depend on how fast I'm running towards you. Okay, but the point is it would be more. It would be then an increase in frequency. Maybe a better way to say it is it would be an apparent increase, because this piece of metal over here would still be shaking at 1,024 times a second. But if I'm moving towards it, I would actually pick up a little bit more. And so I would have an apparent shift in frequency. This process, and let's talk more detail about it, was explained by a guy named Doppler, and so we call it the Doppler effect. And the Doppler effect then is the perceived frequency. And I like that word perceived. It's not the real frequency. This is still the real frequency. This is still 1,024. But as I come closer, it has an apparent change. Now in this case I get further and closer, and it also gets louder and softer, so I hope you don't confuse that. But as I'm coming closer, I'm going to hear more of them. In fact, also the reverse. What if I was running the other way? What if I was running away from the source of sound? And so if I was going this way, what would you expect? Well, then less of them would get to me, right? Because if this is the sound over here and I'm standing right here, I would get, coming by me, 1,024. But if I'm moving away from them, it would be less than 1,024. If I'm moving into them, it would be more than 1,024. In fact, we have a really neat animation here that shows this probably better than I can explain it on the board here. And so let me turn on the display. Oh, and I apologize that I need to pre-warm the bulb. It won't take too long here. Maybe I'll just call up the animation here while I'm waiting for it to warm up. No, maybe I better not, because it starts as soon as I click on it. So I'll go back here and give it a second. Oh, good. It's starting to come out here. And then we'll give it another couple of seconds to warm up. But, in fact, while it's warming up, maybe I'll get my other demonstration starting to go. Okay, now it's looking real bright. Okay. But right here, this Doppler effect, watch what happens when I first click on it here. Click. This is supposed to be the little speaker. This is the sound coming from it. These are the crests of the wave. Here's the ear. And when a wave gets to it, boom, a little red flash goes off. And so this is the rate at which this person hears it. And in my example, it would be 1,024 times a second. But to kind of illustrate, what if the ear was moving? And you can kind of see here, if I make the ear move, see how it flashes a little faster in the red as it moves towards the sound source. And then now, as it's moving away from the sound source, see how it flashes at a lower rate. And so the flashing can change based upon the motion. This is referred to as a Doppler effect. So remember, if you move into it, higher frequency. You move away from it, lower frequency. At least perceived frequency. And it gets even better than that. Well, let me switch the picture here. Let me say, instead of me moving, let's say the source is moving. So I'll put a little S here for source and a little O here for observer. And saying, all right, this is producing the sound. And so when it makes its first pulse, it would go out. Let me kind of draw that right here. And so there would be this big circle around this point. But because it's moving, the next little pulse is together. I mean, it has moved closer. And so instead of them being this far apart, the second pulse is actually closer behind the first one than it would have been if the source wasn't moving. And so what I'm getting at is something that's a little different. And so when the source moves, what we would say is that the wavelength has gotten smaller. But I'm hoping you're seeing that if the wavelength